Okay, the main thing, guys, you have to worry about is the final, okay? Make sure that through this class, if you come in and pretty much through all this week, so the only time you do anything is when you meet me, that is not good. You need for this class, it's very study intensive course. Understood? Very study intensive course. You can practice from anything you want. I mean, it's okay if you practice from any sources that you like. All right, guys. So again, turn your cameras on so I may look at you. I see today we have rather few people. I do not know what's the occasion. It's some sort of celebration today, some sort of holiday. It's called Arkady away holiday. Now let's get on with the material and prepare for it, right? If your question is what's on the exam, it might already mean that you are not doing enough for this class. Everything, anything. Do you understand what we learned so far? No, we do not have an exam soon. It will be by the time we end trigonometry when the exam will be announced. And it will take us a long time to get there because people, I'm trying to give you an opportunity to reach the right level before I give the exam. Many are not on that level. All right, and here we go, guys. So do you remember what we mentioned is the idea of the derivative? Here it is. Again, we want to find a tangent line at the point P. And in particular, we want to find the slope of that tangent line. Yes? And so how do we do that? We simply fix the point P and we slide the point Q towards the point P. You can see here is one Q, it's located at coordinates x, f of x, and I slide it towards P. And you see, when the point Q and point P are very close, it essentially looks like it is a line, one line, going through one point. Good. And the slope, guys, look at it, because it has a very short, the points are very close, there will be a very short vertical segment and a very short horizontal segment. Do you remember what slope is measuring, guys? Slope is just measuring the incline of a line, and it just breaks. If you are walking on a line, the idea is you break the motion into a horizontal part and a vertical part. Okay, so what is a slope of 5? It means that for 1 unit of horizontal displacement, you climbed 5 units vertically. Steepness, precisely. Incline or steepness. You understand, guys, how that measures? It's just by breaking, if you're walking on that line, by breaking the motion into horizontal component and vertical component of the motion, right? And the reason we have the same ratio, what is the ratio? When you say rise over run, that ratio is supposed to dictate proportionality. The idea is this: enlarge the horizontal distance by 2, the vertical distance will be twice as long. Half the horizontal distance, it will halve the vertical distance traveled. You understand it? There is a uniformity of motion. So you communicate it by presenting what remains true, what remains constant. Always the ratio of vertical to the horizontal remains fixed. Because you see why ratio? Ratio crosses away the amplification of vertical and horizontal. You see? I hope you understand what is a slope, guys. Because if you don't understand what's a slope, how can you understand what's a derivative? So then, what can I do, guys? So then I can represent it with those very convenient symbols. dy over dx, where dy indicates that I have a short vertical and dx indicates I have a very short horizontal, as you can see it over here. And this is Leibniz notation. Again, guys, when you think about any ideas, you want to see the lowly origin of that idea, right? So so if you see the lowly origin, you understand it very well, right? So here it looks like you have a limit and whatnot, but all of this fancy expression just should remind you it's just a slope, it's just a fraction, right? And we mark derivatives by saying f prime. We write f prime, that is Leibniz, so that is, sorry, Newton's notation, okay? So then we have two useful formulas for the derivative, which mathematically mean the same exact thing, but psychologically they appeal to us differently. Okay, so here is one way in which I can express the derivative. I can say simply f of x minus f of a over x minus a, and say limit as x goes to a. Okay, that's what we learned before. So what we do here is we say x f of x is that sliding point q, a f of a is that fixed point at which I want to construct my tangent line. So far clear, guys? Let me know if you're confused or anything, so you know, right now we can catch it. Good? Now here is the second notation, guys. Means exactly the same thing. Here, look at what I can do. I can write x as x minus a plus a. Do you agree? X minus a plus a is obviously the same as x. And x minus a is what you have on the bottom. So this I can call h. So if x is going to a, that's the same as to say x and a approach 0. So we have limit as h goes to 0 of f a plus h minus f of a divided by h. You understand what is this talking about? In this version, I am saying that the point x is a perturbation of a. In other words, a slight modification from the point a. It's just another way of saying the same thing. So I'm saying x is like x with a slight imperfection. I mean, x is like a with a slight imperfection, pardon me. You clear? They mean the same thing, but we will see in a moment that you might be induced to perform very different operations when you see one formula as opposed to another. Good? So we can write in Leibniz notation, we can write it as df dx at x equal to a, or simply dy dx at x equal to a. Okay? And here is guys, Leibniz notation is such idea, you see, because Leibniz notation is encouraging a very simple thinking about what the derivative is and its simple origins. In fact, after Newton and Leibniz had an argument, the calculus on the island, on the British island, stalled for about 50 years just because of that notation. You understand what I'm saying? And those were not stupid people. Those are very, very brilliant people, both on the English continent and, both on the English island and on the continent. But you understand what I mean? If you have a very clear, easy way of thinking about it, you can make enormous progress. 50 years. What do you think it does for you if you are not thinking of it simply? So here is, let's try to see what would happen, guys. Let's see, let's try to compute. This is called the derivative. And if you remember what it's called in German, the derivative is called, I'll write it for you. It's called Ableitung. Ableitung, which means off lead, roughly speaking, right? If I wrote lead correctly. It means basically, because think about what it means in physics. When you travel along a curve, if the curve is not a straight line, that means there is a net force acting on the traveling body, on the particle. Good? You understand? And what happens when the force stops? You depart. The particle departs from the curve along a tangent line. So that's off lead. That's why I like the word Ableitung. It also reminds you what a derivative is, what its significance might be. Again, guys, It's nice to see you all, and as many of you as possible, consider turning the cameras. I should warn you on the final, because I noticed that you already are forming some groups and other things like that. I might monitor you also on video, because cheating will be prosecuted severely, mercilessly. So consider developing the habit of being on my good side. I want to see who you are. I want to see what you do in this class. So when you can, turn your camera. On the final, that might not be an option. So here we go, guys. F of x is equal to minus 2x squared plus 5x plus 13. I want you to compute the derivative at an arbitrary point A using notation 1. Notation 1 is this notation, you understand? The old one. And notation 2 is this one. Okay? Here, so that you may stare at it, I might, let's see, what is this? Minus 2x squared plus 5x plus 13. I'll write it here for you, just so you can look at it. I want you to compute f prime of A, where the function is f of x minus, what did I say it is? Minus, my memory is like that of a goldfish. Minus 2x squared, yes. Okay. This is your function. I want you to compute the derivative using notation 1 and using notation 2 and see if there is any difference in what you are doing. So first do it using notation 1 as we did in the last class. Very good, Christiana. Humira, beautiful. Exactly. Faza. Amazing. We have now, I hope you're actually doing it, guys, and not copying the first person, right? So if so, then that's good. All right, so a bunch of you did it, guys. So let's look at it together. And by the way, guys, you should train. It should be so fast for you that you can do it in 1 minute. Question like this, by definition, not with a shortcut. 1 minute, and it's generous. 1 minute. Good. Let me explain to you what you do. So using notation 1, look what you do, guys. Here is the setup. So it's limit as x goes to a, the function at x minus the function at a divided by x minus a. Do you agree? Now, what I do next is I group like with like. And you can actually skip a lot of steps. You understand? I would right away know if it's minus 2x squared. I know that when I simplify, it would be minus 2, parentheses x squared minus a squared. And if the next term is plus 5x, I know that when I simplify, it's going to be plus 5x minus a. You understand? So let me just quickly show you what happens. Imagine that for a moment the function was much more ugly. Imagine the function looked like, well, let me clear it here. Let me write it on a separate board. Imagine the function was something like this. Minus 7x cubed plus 4x squared plus 3x minus 12. Yes? So if I did the derivative, I could right away, using this procedure, the derivative at a would look like this: minus 7x cubed minus a cubed plus 4x squared minus a squared plus 3x minus a divided by x minus a. I can right away write that step. You understand? Just look at the pattern. That's exactly what happens. You group like with like and factor the constant out. Make sense? Right? I could get to that step in just a few seconds. You can see why it happens, guys. Yes, minus 2x squared minus 2a squared. I keep this minus, I can factor out the minus 2 here. Good? Next, I will factor x squared minus a squared, and I see that there is an x minus a, which you see that I can factor out. You see this? And do you see this? It's the same term. I can factor it out, and what I'm left with is minus 2 times x plus a plus 5. Yes? And I can factor out x minus a, whereby it's possible to cross it out. Clear? Right, guys, here, I mean, how do you train? You just have to practice. Yeah, you have to kind of be good at that basic step, right? And then I push limit as x goes to a. So what happens? Here we have x, it's becoming a. So it's minus 2a plus a, which is minus 4a plus 5. Minus 4a plus 5 is the right result. And we're done. We're done. Now, would you try? It's good, just one experience. Try to do the same thing, but use the other formula. Do you remember the other formula? It's just this. Notation 2 is try to calculate limit as h goes to 0 of a plus h. Good? Remember how we obtained it, guys, right? So always think, how was that formula obtained? Here we are speaking about the other point. We are indicating that it's very close to a. So h is going to 0. Now try to calculate the same thing with that other formula and see how long it takes. And what do you do? Scroll up, sure. But if you had that written from before, here is that function. All right. Well, obviously the answer will be the same. It should be minus 4a plus 5, but my point is not the answer. My point is how long does it take you to carry this procedure? And which of those two procedures is better? I want to ask that. You understand? Which of those two procedures is better and why? So notation 1, Anna, you're saying, right? Okay, notation 1. Okay, let's try to look at it, guys. Not less calculations, but less, well, it depends what you do. Let me now show you what happens. Are you ready, guys? So let's see what we might do if we carry out the second procedure. Now, if we write the second procedure, it's instead of the first part, it's f at a plus h. So we have minus 2 times a plus h squared plus 5 times a plus h plus 13 minus the function at a. Then I expand, I multiply the 5 through, simplify, and I get at the end of the day after simplification, I have minus 4ah plus 5h minus 2h squared. I divide by h and take the limit. All right. So notation 2 psychologically compelled us to expand the parentheses and distribute the terms. And you can see that it takes me longer to write. It's bulkier. Okay, so it's bulkier and you're writing more symbols. You see, if you write more symbols, you have to process more things. So just let me show you what happens without even bothering to carry out the calculation. Just see how many symbols we obtain when we use notation 1 with this function. Okay, when we use it with this function and I use notation 1, I can calculate that I just by writing it once, I had written 33 symbols. You can count them if you want, 33 symbols. You understand? Now, if I use notation 2 for the same expression, that expression, don't worry, I'm not asking you to carry the limit, just look at how many symbols are used. Just writing it once, I wrote here 43 symbols. Do you see what happened? That's writing it once. Every time you write it, you are writing, and actually going to be much more, because when you expand, multiply, so there is in this case degree is 4. Expanding degree 4 will create a lot of symbols, but in the very least, each time you write it, you're writing extra 10 symbols. You're already slower, and it's bulkier and it's harder for you to grasp through one look. What do you call it? In one swoop. Okay, so you understand what I just what we just explained, guys. I hope you do understand it, right? So you're not very experienced with doing it, but I hope you understand that it matters which notation, even though they mean exactly the same thing, it matters which notation you pick to carry out this operation, because if you pick the second notation, you will carry the calculation longer. You are much slower and more likely to make mistakes. Okay, sometimes we will see the situation notation 2 is better. Anytime, that's my so to speak advice for any algebraic function, that is for any function we have considered up to this moment, notation 1 is better than notation 2 if you have to think about the derivative. Of course, that depends, of course, what you're trying to do. Good. There is a situation, and you will see it later, that if you stick with notation 1, you are not likely to make any progress. But if you make that small change and use notation 2, you will make tremendous progress. And we will see that later. You understand? So it's not that notation 2 is useless, but for polynomials, pick notation 1. I notice, by the way, when I have exams that most people do not listen to me. They carry out the calculation correctly, but they do not listen. This is a better notation. Good. So if you think, you will say you will save a lot of time. So let me show you what happens, guys. So first, I hope you can recall. Let's see if you can find the derivative of x squared. The function is f of x equal to x squared. If you calculate the derivative, it ends up being 2 times a. You understand? So if the function is x squared, the slope at the point a will always be twice that point. And you can try carrying out the derivative for root of x. Let me just let's see how you do it. Could you please, guys, before I move on, if this is my function, could you tell me please what is in general f prime of a? Calculated. If you are bored by this question, here is another one, guys. G of x equals to 1 over x squared. I want you to tell me what g prime of a is. All right, Humira, correct for F. Karen, you made a small mistake. It's not 1 over the square root of a, it's something similar. Okay. Fast, guys, faster. All right, good. Let's look at the first example, guys. So first, f prime of a, its limit as x goes to a. I mentioned that I prefer this expression for all algebraic operations, right? So I will use x goes to a, and I will write root x minus root a divided by x minus a. By the way, if you will allow me, guys, I will do it instead of conjugating, I will do something else just to show you what will be the situation later on. Okay, you can multiply by the conjugate, but you can also factor the denominator. You want to see? Because what is the denominator? The denominator is root of x squared minus root of a squared. Good? You understand? Instead of doing the conjugate, I'm actually factoring the denominator this time. And so what do I get? I get limit as x goes to a of, I can, you see, if you allow me to cross it out, this is just root x plus root a times root x minus root a. So I'm left with root x plus root a. And here we have 1. And so the result is 1 over root a plus root a, which makes it 1 over 2 root a. What I just obtained, guys, is now I know how to calculate the slope for any point. If it's at the point 1, I just take root of 1 and multiply by 2 and take the reciprocal. Right? 1 over 2 times root 1. If it's at 4, I just take 1 over 2 times root 4. Do you understand? So I solve the slope simultaneously for all points. Now, do it for 1 over x squared. Let's see if you can do it for this function. Go ahead, calculate. Francis, you made some mistake. It's close, but not quite. Yes, Christiana, very good. Very good, Robert. All right, guys, let's do it together because we still have a lot to go over. So here is the situation. So this is by definition limit where x goes to a of 1 over x squared minus 1 over a squared divided by x minus a. Yes? Now I should advise you to write it like this. Now I can first of all write a common fraction here, right? So what's the common fraction? It's a squared minus x squared divided by a squared x squared. Do you agree? I just, this one had to be multiplied top and bottom by a squared, this one by x squared, so that I may be able to combine the denominator. So this is my numerator. Yes. Now I divide by I divide by x minus a. That's the same as to multiply by 1 over x minus a. Good. Now that's the same. What is a squared minus x squared? I can write it as minus parenthesis x minus a, x plus a. Do you agree? I factor the minus, it becomes x squared minus a squared. Yeah, thank you, Gabi. So if Gabi, if you you continue doing what you do, and I will help if you would look at it later. How do I get this? So I just simplify a fraction. Look at it. 1 over x squared minus 1 over a squared. What do you need to do? You need to multiply this by a squared and a squared to get the same fraction, and this by x squared and x squared to get the same fraction. Good? You understand, guys? Or do I need to tell it in German? So we have this. You understand how I factored? A squared minus x squared is the same as minus parentheses x squared minus a squared. Good. And then multiply by 1 over x minus a. And of course, then I can cross away x minus a. And now I can push the limit as x goes to a, no problem. What do I obtain? I obtain, look at it, guys. I obtain here minus a plus a, so that becomes minus 2a divided by a squared, which I can simplify further. A cannot be 0, right? This will not work if a is 0. If I simplify it further, it becomes minus 2 over a cubed, and I'm done. All right, guys, I want to know, by the way, how many of you, I'm sorry if it's an intrusive question, how many of you took calculus before in high school or some semester ago? What I'm interested in is because some of you might know shortcuts, right? Some of you know shortcuts. And I always have those questions. I mean, you see, there is a very quick way of doing that, right? Why am I making you go through this procedure? Any ideas? right? So, I mean, there is a I will teach you the shortcuts later on, but why do I not do it right away and I make you do the definition of the derivative? And then some other people say, well, here you go, Robert, right? That's obviously part of the answer. Okay, that's part of the answer. I do enjoy when my students suffer very much, right? It's the bane of my existence. But there is yet another reason for it. So somebody even asked me even a better question. You know, you can make a computer do it. Ask the computer what's the derivative, and the computer will calculate it and do it much faster than any of us can. Right? Why not just plug it into a computer or scientific calculator? I mean, I hope, guys, that you will see my point. You know, you see that what we're doing right now, we are learning vocabulary. You understand? You think of it as like you are learning particular symbols or particular parts that if you can understand them, you might have a chance to read a very interesting book. Okay? The point is, I can show you what you can do. I mean, there are many functions, many ideas that nobody taught me, and nobody teaches those things. It's just you right away come to them if you think in terms of this material. Understand? It's supposed to be an enhancement of your thinking. You can obviously do that if you look at physics. When you study anything in physics, you have to come up with your own formulas, with your own theorems, with your own conclusions that, you know, there are too many of them to be listed in a book. You understand? So what we're learning, I don't really want to calculate those derivatives. What I want to do is, if you understand how they work and what they are, you will be able to think using those ideas as crutches. You understand? I hope you will, guys. It's a sort of, I mean, I cannot give you those examples because you would just not understand them. I will show you later on how many ideas does it take to solve even a basic physics problem. Okay? And not just a physics problem. You have all sorts of other things. Good? Besides, guys, if you do it my way, you will actually, the subject becomes a grain. It's going to be so little and so much the same question, as opposed to like the book is what 500 pages long, right? The idea can be summarized in one page if you understand it. Okay, so you're distilling it anyhow, guys. So let's get back to this process. You see, we notice that in essence the derivative is another function, and we might now make another switch, right? It's not convenient for us to switch from x to a, right? Let's say I want to know what's the derivative at the point x. I now change my notation. So now x takes it's no longer the moving point, it's now the fixed point. So f prime of x using notation 1 is limit as z goes to x of f of z minus f of x over z minus x. And the second notation is the limit as h goes to 0 of f of x plus h minus f of x over h. You understand what I'm doing here? The reason is this, look at it. Look at it. If you have the function f of x equal to x squared, right? I would say f prime of a equal to 2a, right? So, but why do I switch from x to a? So I want to say f prime x equal to 2x. Okay, I don't want to make the switch to another letter. I just want to keep x when I take derivative. You understand? To make it a function of the same variable. Okay, so that's the slope at that fixed point x. You have to be very careful, naturally. So, for instance, guys, let's see if you can do it, guys. Do you see this? This is also the notations. X squared plus 3 times root of 9 minus x. It's a little bit hard. Christiana, so here is again, in terms of your final, guys, in terms of any exam, you look at the question, you see what is asked. If you're asked find the derivative, it doesn't matter how you find it, right? As long as the answer is correct. right? If you say do it by definition, in other words, they're checking whether or not you understand what the derivative is. You have to do it by definition. You understand? By definition, meaning using notation 1 or 2. We will learn shortcuts, but we will, right now we don't have them available, right? Right now we are at the very, very beginning. Here, guys, I'm going to ask you a much harder question. I want you to calculate the derivative and actually keep x. This is my function, find me the derivative at x using any notation you like. Right? As I wait, I will go exercise since I'm bored here. Okay, see you soon. Okay, wonderful, Christiana. Zvi, beautiful. All right, 2 people have it. Come on, guys. 2 more minutes and I will discuss it, okay? Wonderful, 3 people now. Okay, 4 people. One more minute. All right, let's do it together, guys. Ready? So here is the setup. You see, I make Z go to X because you see now I want X to be that fixed point. F prime of X will be what? So it's Z squared plus 3 root 9 minus Z. I use notation 1 because it's nicer, okay? It's nicer for this type of problem just because it uses fewer symbols. And I push the limit as Z goes to X. And do you see I group like with like? So Z squared and X squared, 3 root 9 minus Z and 3 root 9 minus X. And you agree that I can break it apart. So I have 2 fractions. Do you see how I do it, guys? I group Z and X and divide by Z minus X. And I group 3 root 9 minus Z with 3 root 9 minus X and divide by Z minus X. Limit of the sum is the sum of the limits, and I can write it like this line. Are you with me? You understand, guys? Just basic fractions. Z minus X goes to Z squared and X squared. Z minus X goes to 3 root 9 minus Z and 3 root 9 minus X. Here it is. Now the first part is easy. I can factor out Z minus X and simplify. And here I decide to multiply by the conjugate. You see that? Once I multiply by the conjugate, denominator I don't bother. Numerator simplifies. Look at it. Numerator simplifies into minus Z minus X. You see? 9 minus 9 is 0. Minus Z minus X is minus Z plus X. Factor the negative 1. And you have minus 1 there, right? Don't forget the 3 in front of the limit. Now push the limit. You will get 2 root 9 minus X. Because this Z will become X. Guys, are you with me? All right, you see, guys, it is, I try to explain it as briefly as possible. All it is of course, I mean, you have to kind of get used to the basic algebra, right? It's just basic algebra, right? So just very simple. Look at it. Set it up, be efficient about it, and then you can cross away z minus x, and you get 2x plus minus 3 to root 9 minus x. Okay, and now we can examine the relationship between the graphs of f and the graphs of f prime. Okay, well, the relationship is very important, guys, and I will try to tell you how I think of it. Well, Francis, it's nice to move slower, but if you have any particular question here, I can try, but I have to move at a certain speed, believe me. That's why the first exam is very delayed, and that's why we somehow always have to cram the materials, because I try to cover not only the current material but also your gaps in knowledge from before, which is beyond the class. So you have to train and read and study a lot and do it. I mean, you know, when I studied calculus, I studied 4 hours a day. I did it myself. I taught myself the subject. So what you do is you should do the same thing naturally, right? You just you solve a lot of problems. 4 hours a day is what I did. Good. All right, guys, here is now, let's try to talk about this relationship between the derivative and the function, okay? So imagine that you have a differentiable curve and you are zooming along this point P, right? What will you begin to see? When you zoom in at a function that looks like, well, that looks like it would be differentiable. Maybe I should try to come up with some animation. Let's see if I can do that. Here it is, guys. You see? Here is a graph of y equals x squared. Now you see I'm zooming in. Do you see what happens? Look at it. I'm zooming in at 0, 0. And what do I begin to see? Look at it. Are you with me, guys? What do I see, guys? It looks flat. Wasn't it amazing? It looks flat. In particular, it looks like a horizontal line. Yes? It looks flat. You see that? Now, let me zoom out for a second. And let's select a different point to zoom in. Let's say this point. What are you seeing? What are you seeing, guys? It looks like a straight line. Do you agree? Now notice, you see that if you zoom in anywhere else, let's say I zoom in here, it looks like a different line. Do you agree? But no matter where I zoom in, it looks like a straight line. Why is that? Would you have predicted that it would look like a straight line if I did not graph? Without seeing the picture, would you have predicted that? You would not have predicted that. Okay, guys, here you go. And the reason that you're not predicting it, it means that you don't feel the derivative enough. What is a curve? Let me try to remind you what is a curve for a second. Now, why are we so concerned with the derivative? The derivative is just the slope of a line. Why are we so concerned with lines, guys? Could you remind me? Why lines? You see, that's what I mean, right? That's a question. Why are we concerned with lines? So when you say line makes up greater shapes, maybe rephrase it, Robert, and maybe it will be good. You have to have a very crystal clear description. Then you understand what you're doing. Come on, guys, tell me why. Lines can be defined by 2 points. Good. So line is the simplest object. Good. And suppose that our interest is in describing other curves. Other curves, right? So how would you? What do you think of? What is another curve? What does a computer do when they draw a curve, right? So a computer can do something like this, right? So here is, let's say this is my curve. Okay. What can a computer do? A computer can say, this is a straight line, and then this is another straight line, and this is another straight line, and another straight line, another straight line, another straight line. Just imagine those lines are connected. Do you see? So I can think of my graph as many microscopic line segments attached to each other. So when I zoom in, I just make a microscopic line segment look large. You agree that guys, do you agree that you could have drawn a curve that looks essentially the same like what I did with a smooth motion by just connecting tiny microscopic lines? So what is the derivative doing, guys? What we're calculating when we take the derivative, we are calculating the slope of the local line, of the microscopic line segment that builds that part of the graph. Do you understand? You can think of the motion, that's what the computer does, as just sequential motion of small line segments, right? And in the limit, those line segments are smaller and therefore fit along the curve much better. You understand? So you're again building, like that's what I mentioned, you have this Lego block analogy. You're building the curve out of Lego blocks. And if you understand that idea, guys, you understand precisely what it is that we're doing. Okay? We're trying to understand all curves in terms of straight lines and see how far can we take that analogy. Are there curves that are not like straight lines at all, that cannot be built up of lots of straight lines? Okay. But if the derivative exists, the derivative is signifying the slope of a local segment, of a local tile. Good. Now let me try to explain, guys, that and this is what the limit is doing. Now, why when I zoom in, I see a straight line? Why do I see, and what straight line do I see? Good. The straight line that I see, I hope it's not a mystery, is the derivative. Do you agree? It's the derivative line segment. It's the tangent line that I will see. You understand? The tangent line to the curve is what I see when I zoom in on the curve. Let me try to explain why that's the case. I hope you understand, guys. You just have to imagine a little bit. Okay. So imagine that you are a microscopic creature compared to that curve. That, by the way, is very important, guys. You understand that well, even somebody like Martin Luther thought it's a preposterous idea to imagine that the Earth is a ball. But you understand why does the Earth not look like a ball? Because compared to the Earth, we are very small. And if the Earth was a perfect ball and you were to be very small and zoom in at a particular point, it would look to you like a plane. Anywhere you zoom in, it would look like to you like a plane. Do you understand that? The effect is the same effect that what happened when I zoomed in at some other curve. Clear? Now let's see why that's the effect. So I think of it, guys, as a bouquet of flowers, okay? So suppose you're zooming at the point P, okay? So look at it. This is your view right now. At the point P, what I imagine is that from the point P, you can extend lines to all the parts of the curve that you see. I consider it all possible. So from point P to any other point on the curve that I can see, like the edges of my screen, I can extend a line. Let me possibly show you here what happens, okay? I'm hoping that will be clearer. Okay, do you see, for instance, guys, for instance, let's suppose that I'm interested in that I'm zooming at this point, right? Let's actually make the screen centered. Let's make the screen center, more or less centered here. You see that, guys? Suppose that I want to zoom in at that point. Now, right now, it does not look to us like a line. Why? Well, because look at it. I have this point P at which I zoom in, and I can draw this line. It connects at this point, right? Or I can connect this point, yes? Or I can connect that point, right? So I have a bouquet of lines, I call it, a bouquet of lines. That's why I drew it like flowers. And they crisscross, right? The bouquet of lines, there is a lot of crisscross here, right? Different slopes, do you agree? The slopes are different. What makes it crisscross is that the many slopes that I can create are different slopes. You follow me? Now, what happens? Look at it. So what is that point? That point is, this point here is some point x squared. Do you agree? For the parabola. It's x squared. Now, x squared is still far from the point 0, 0. Yes? That's why you see it, because what happens? When I measure slope from x squared to 0, 0, I can get lots of slopes. You see, when you say f of x minus f of a divided by x minus a, that's a slope at a particular x that you selected. You follow me? Okay, guys, it's very important. You see, if you do, then you can see a lot of marvelous things. Now zoom in. What happens when I zoom in, guys? What happens when I zoom in? It's the same as if I bring the x close. Look at it here. You can see x can be 3. Do you agree? Now look at it. When I zoom in, do you see now x cannot be 3? I don't see 3. X cannot be 2. I don't see 2. Right? Look at it. Here is 1. Do you see that? I zoom in, and now x is, let's say, between, well, let's make it center. So now x is between, roughly between 0.6, minus 0.6 and 0.6. You see, minus 0.6 and 0.6. So x is close to 0, right? When we calculate limit, if x is close to 0, what we're getting is essentially we're getting the tangent slope. But what it means is that for any x you select in this interval, it's going to be close to the same slope as if the points are near 0, right? Look at it. Do you see that? You see what's happening? Now x cannot be here, right? X cannot be very far from, look at it, here is, if I make it between minus 0.2 and 0.2, that means x is very close to 0. And in any x I select, you see, now I'm allowed to select only x's here. So calculate slope with this x or that x with 0. The slopes are almost the same. They become uniform, you understand? I delete slopes that are deviating from one another, and the bouquet of flowers becomes, you see that the crisscrossing becomes very narrow. The angle of crisscrossings becomes tremendously narrow. Yes? Do you follow? So that means that when you zoom in at any particular point of the curve, it will look like the tangent line, because the slope becomes that of the tangent line and it passes through the curve. Do you understand? So geometrically, so it's almost like a computer science. Think about, why does it feel natural that a particle continues on a tangent line? It's like the particle forgets that it needs to switch from one segment to another and continues on that segment of the curve where it was moving. What can you do with this information, guys? Well, you can construct a roller coaster. You can understand what it means to measure energy. When you ask yourself, energy, is it an important concept? Is momentum an important concept? Do you understand, guys, philosophy, right? Have you ever thought about monadology? Leibniz, a philosopher, right? And a mathematician, he said that, for example, when you want to move your arm, let's say clench it into a fist like this, right? You have the soul desires the clenched of the fist, but that's not causing the clench of the fist. Are you following me? It does not cause the clenching of the fist, but rather that the body and the mind are synchronized. So he thought of it like two clocks that are synchronized. You see, the fact that my left finger moved to the left, and the fact that the right finger moved to the left, it's not cause and effect. They are just synchronized. So he thought the soul and the body are synchronized. Now, can you tell me? Can you understand why he thought so, or why at least he claimed that to be the case? You know why? So your body just is in synchrony, but it's not caused by the soul. Because already at that time, a long time ago, they understood that there is a conservation of momentum. And you know what conservation of momentum, it has to do with derivatives, it has to do with what I'm explaining to you. That means that if I, in theory, know the position of every body, of every particle in the body right now, and the velocity with which the particles are moving, I will be able to predict where you will be in the future and where you have been in the past. You understand? I can predict your entire history and your entire future. That's the consequence of mechanics. And that means that there is no purpose for the soul. The soul is meaningless. And if you are a religious person, then he has to somehow justify, of course, in a very redundant and unnecessary way, but try to justify the existence of an immortal soul, and that immortal soul does not seem to be able to interact with physical objects at all. You understand? Based on at least the theory of mechanics. That's a consequence that you can understand when you study this. And when you ask, of course, you might not be religious or not care for philosophy, guys. Much of what exists around you has to do with those ideas. You understand? Physically, what it has to do is just building blocks, right? You can, for instance, construct a roller coaster and predict how the roller coaster will move by understanding how it moves along a segment of a straight line. So the consequences are enormous. The consequence is modern physics, right? You understand? Modern physics did not, and if you study calculus without, if you study physics without knowing calculus, I do not believe you understand physics at all. And I can show you good books for that, right? Not even mechanics. So it's written right now, it's written in the language of calculus. It was brought about scientifically for the purpose of describing physics, describing motion, describing everything you see around yourself, and maybe failing to do so at some point, right? But the idea is a modern idea. It still is the idea that you are using today for any description. Okay, so calculus is, I mean, there's a long argument. I'll show you some other interesting examples. There's a long argument what is necessary for what, but anybody, any engineer, anybody who is good at those things understands those ideas well. Okay, I mean, you can argue, do they understand it because they're smart? They just kind of understand all of it and that's how they communicate, or is it necessary to understand those ideas in order to do it, right? I think it's definitely a very convenient way to communicate. It's like asking, what's the purpose of language, right? People were in the cave. They, you can preserve information this way and transmit it effectively if you have the right language. Good. What you're learning is perhaps the best and most interesting thing you can learn in college. One of them, right? I mean, you take a lot of subjects which are completely meaningless, completely unnecessary. This is not one of them. I hope you see that. Right, so I suppose unless you're taking a very advanced physics or some very amazing, something extremely intellectual, this is the most important class you're taking. Everything else you can kind of do without school. Even that, I mean, if you read. So good, back to this topic. Do you see the bouquet of flowers? So you understand now what I mean by that. So the flowers, they are now, their angles between them is very small, and that we know because we understand what the limit means. And nobody needed to tell you that. You see, if you understood what the derivative is, you know that when you zoom in at the curve, it will start to look like a straight line. And that straight line is the tangent line. Clear? Beautiful. And here is my illustration. So this red triangle represents the bouquet of flowers for the red point of view. And then when I zoom in and I shrink the possibilities for X, the the flowers are now tightly packed together. They make shorter, smaller angles relative to each other. Good. And this is, so the equation of the tangent line is the graph that you will see when you zoom in at any differentiable curve. Differentiable curve, guys, means that it's a type of curve that when you zoom in locally, it looks like a straight line segment. You understand? So it's something that's it's a chain of lines. So here is that observation again. If it's differentiable, it locally looks like a straight line. If you zoom in at another point, it would look like a different straight line. Do you understand? With a different slope, depending where you zoom in. So here is, guys, let me see how good your understanding is. So I'm making a claim. If the function is differentiable at a point A, it is also continuous at that very point. Can you, then anybody, can you explain to me why that's obvious? Differentiable, it's continuous. If the function is differentiable, then the function is continuous. Why is that obvious?
To me, it's obvious because if we zoom into that specific point where x is going to be equal to a, we will see a line.
Yes, that's beautiful. And if you see a line is a connected graph. You understand, guys? Continuous function means its graph is connected. Now, a line is obviously a connected graph. Yes? So, I mean, it's like, you see, if you understand that idea, then it's trivial. Of course, it would be continuous. Right? Because if it were ripped apart, when you zoom in, if at a point it's ripped apart, when you zoom in, you see a hole, you see a gap. And that is not a straight line. Yes? Beautiful. Beautiful, because it is a line. Of course, guys, this is just intuition. We always have to prove things as much as we possibly can. And as you get more sophisticated, you get paranoid because you are so often tricked. You get paranoid and you have to prove things because sometimes you might be convinced of an idea and the idea ends up being false. So here is that situation, guys. So the result is obvious because zoom in at the point A, you will see a line and its slope will be the derivative slope. You understand? Now let's do that mechanically. In other words, let's do that by analyzing the limit to see that the limit shows us that it's continuous. Good? So here is how we do that, guys. What does it mean to show that something is continuous? Do you remember? It means show that limit as x goes to a of f of x is equal to f of a. You understand why? Limit as x goes to a of f of x means that if I select points closer and closer to a, the sides of the curve merge together and merge to f of a. That's how I indicate that the graph is connected. You understand? Functionally, when I evaluate the limit and I get the same result as plugging in the value a, that means the curve is connected. You agree? Guys, you're not bewildered yet, right? You all see what I'm talking about. Or are you, oh, what the hell is he talking about? Christina sees it, but what about the rest of you guys? 28 people. Can I show what? You have to, guys, play it in your mind. Play it in your mind, guys. You see, it's an exercise. Another thing it does, guys, it's an exercise in imagination, right? Make your brain imagine. I mean, you see, those things are descriptions. If you, let's say, why would you enjoy a book? You enjoy reading a book because you can actually imagine what's written there. And if you don't imagine what's written there, if you don't process it, then you don't enjoy it. It's like you see blackness. Right? So do you understand the reason that continuity is defined as limit x goes to a f of x equal to f of a? That means that f is continuous at a. Do you all understand why that's the case? I spoke about it before. Yes, guys? You see what they say? Guys, if you don't, then you forget this idea instantly. Yes? What does it capture? It means this idea, guys. You see, so it means that here is my graph. Here is the point A. If I walk x towards A, either left or right, it will merge at the point FA. You agree? move your x is, as you move your fingers, x f of x should move closer to a f of a. That's continuity. Good? You follow me? So now let's see by definition, guys, why differentiability implies continuity. So assume f prime a exists. In other words, that that means that when you take the derivative limit, that limit will be f prime a. Okay, I want to see what is limit as x goes to a of f of x. Okay, you see, I know what I want. I don't know how to interpret the limit of f of x, but I know how to interpret the limit of f of x minus f of a over x minus a. So then I use wishful thinking, you see, which I have because I know what I'm trying to see here. I'm trying to see the expression for the derivative in here. So what is that, guys? Limit of f of x is limit as x goes to a. Look what I do, guys, of f of x, and I'll change color, minus f of a plus f of a. Do you understand why I added why I subtracted f of a? Guys, do you understand what's happening in my head? I am trying to reconstruct the definition of the derivative, because that I know immediately what to do with. You understand? If I know where I'm going, I am not lost. Right? I don't want to see limit as x goes to a of f of x. I want to see f of x minus f of a over x minus a, because that's a limit that I'm guaranteed exists if the function is differentiable. Yes? And so what do I do next? And so tell me, please, guys, what is my next step? Look at it. I did this. If you understand what I'm saying, what do I do next? Divide by x minus a, exactly. But if I divide, I have to multiply. I cannot change the expression. Very good, Francis. Amazing. Divide by x minus a is what I want. So look at it, guys. So I will write that next step. So here I write it f of x minus f of a. And here I want to divide. I'll write it in blue, x minus a. But if I divide by x minus a, I must multiply by x minus a, since I did not have it to begin with. You see? I wanted to divide, but to balance the expression, I multiply by x minus a. And here we have plus f of a. Now, what would that limit be, guys? This limit here, it's a limit of a product. This limit becomes f prime a. This limit here becomes 0. So it's f prime a times 0 plus f of a, which is f of a. You understand what I just did, guys? Without any visuals, without anything, I proved that the formal definition of continuity is established from the definition of differentiability. Right? And of course, to be able to think like this, I need to be comfortable with all those formulas. I have to be comfortable with the derivative definition in its original form. Clear? You see, what we established geometrically, we just saw it, but we also established it analytically by just working from one definition to another. Clear? Guys, how many of you understood my explanation just a moment ago? Both of them, the geometric and the formal, the analytic, the algebra here that I carried. Yeah, I know, Christiana, you did, obviously. The rest of you? Okay, 70%. What is the 30 that we're missing, Francis? I don't see a lot of you writing, guys. So are you very confused? I'm waiting. The graph. Okay, Francis, what do you mean by graph not clear? Which graph? If you mean the picture for continuity that I drew here, that is just, I'm trying to explain here why the definition of continuity, how is it supposed to capture the idea that the graph is connected at that point? Yes? So guys, you all understand the definition of continuity. Like 10 years from now or 100 years on your deathbed, your grandchild asks you, what did you learn in calculus? At the beginning, you would say, it was continuity, right? And you would do this before you die. Yes? Am I right? And then you understand that continuity implies differentiability, correct? I mean, sorry. I need to wash my mouth with soap. Differentiability. Blasphemy, right? It's terrible. Differentiability implies continuity. Yes? Why? So not lines. Be careful, Francis. When you say lines move closer together, you can confuse yourself with your own words. What it means is that if you move the point X towards A, here is A, right? Here is that picture. If you move X towards A from either left or right, the position on the curve will move closer and closer to f of A. X is anywhere you like. Where do you want to move? X going to A from here or X going to A from here? X is not a particular point. X is meaning, it means this. Pick your X position, your position on the X axis closer and closer towards A, and your Y position will move closer and closer to f of A. That's what continuity is supposed to signify, okay? And the idea is that if that happens, that means that the curve is attached at the point AF of A. At this point, there is no break on the curve. Good? And you understood this idea, guys, right? So this is how you prove that differentiability implies continuity formally, right? Informally, which is amazing. You just say, okay, it must be a straight line. When I zoom in, I understand it will be a straight line, which is also an understanding of a limit, yes? Right? Because what happens when you zoom in, you are zooming at a particular point. And when you zoom in, the axes that you can see in your picture are very close to the particular point, which means the slopes from that x to that point will be very close to the derivative slope. Do you understand how I'm reasoning, guys? You will not forget that, right? You have to repeat it, and you have to really repeat it so that it's clear in your mind, because when you use incorrect words, afterwards it's going to be corrupted and you don't remember it. This topic is called derivatives, precisely. It's the beginning of it. So it's the slope of the tangent line, the derivative, and whatnot. Okay, good. Let's move on. I hope, guys, you understand. I mean, it bothers me maybe more than it bothers you, right? When I think, oh, you forgot it. This is that definition. Then we have limit is okay. Now, next question, guys. Is the opposite true? Does continuity imply differentiability? And explain to me before you answer that question, what is that asking? When I say continuity implies differentiability. So when you say yes or no, I also want you to be able to explain to me. I would really love if you speak with me, guys. So you can tell me in words, what is differentiability geometrically and what is continuity geometrically, and why or why not continuity implies differentiability. Okay, Francis is asking again this question. What does differentiability mean? Would anybody here like to say it, guys? Please don't be scared. Speak, turn your mic, speak. Who wants to do it? Don't volunteer all at once.
Can I explain to him, Professor?
Go ahead, try, Christiana.
So I think he's confused like continuity and differentiability. So sorry if I'm not pronouncing correct, but I understand that continuity is a function where all the values of that function form a graph, which is a continuous wave or like a curve. And differentiability is a function where the derivative exists at each point of that specific function.
Yes. but maybe people forget the word derivative yeah. So guys, so let me try one more time a little bit, right? So differentiability means what? Means the graph locally looks like a bunch of line segments, right? So you look anywhere, it looks like a line segment. Do you understand? Continuity means that the graph is one connected curve. Okay, that's in terms of the picture. Continuous graph is one connected curve. Differentiable graph is one that looks like it's built of line segments. When you zoom in, you are seeing a line segment. Now the question is, does continuity imply differentiability? And what does it entail? So Christiana says no. What about the rest of you? Okay, Francis says no. Now if you say no, what do you mean? So how would you observe a continuous graph that's not differentiable? What do you do, guys? Imagine you're saying, oh, this graph is not differentiable. How would you visually explain that it's not differentiable? What would you do?
So I understand, like, if we zoom in a continuous like curve, I don't think we see a straight line. It will be like a curved line.
Well, it would not be a straight line. That's very good. That would not be a straight line. You understand, guys? So if you are claiming that there is a continuous function that's not differentiable, there will be a point, and if you zoom in at that point, it will look nothing like a straight line, no matter how much you zoom in. Clear? Okay, let's see if we can find such a function. Would such a function exist? Well, let's look at it, guys. Here is an example of a function where that would happen. Imagine just taking two line segments and attaching them at a rough angle. Just take two line segments and attach them at a right angle. You form a picture that's continuous. You agree? It's one connected piece. But if you zoom in at the peak, it remains sharp. Okay? So differentiable functions are also known as smooth functions because they're kind of nice to the touch. Okay, you don't have sharp edges. You follow me? So that's an example of a function that's not differentiable. And here is a worse example, guys. Do you see that this is a worse example of a non-differentiable function? Here, look at it. Here, the angle between the two lines is how should I say it? It is a particular, it's a fixed angle. Whereas if I wedge it like this, then the angle goes to 0. So this is sharp and this is extremely sharp. Okay, in this curve you can see that the derivative, if you approach from the left, it will be positive infinity, but if you approach from the right, it will be negative infinity. Okay, maybe I can try to see if I can plot something like maybe graph ups. Let's see if it understands it. Didn't graph it. No, you cannot graph it, I think. Okay. Why does it being sharp matter? Let me for a second show you maybe this. Let's see, absolute value of x cubed. I mean, without absolute, just x cubed, sorry. Yeah, I wanted to, it's of course not x cubed, sorry. That's why my mistake, that's why it didn't work. I meant 1/3. Here, you see what's happening? Look at it, guys. So let's zoom in over this point. Do you see? It looks like a straight line when I zoom in, yes? Now let's zoom out for a second and let's see what happens if I zoom in at this point. You see that the line is steeper, right? Now let's zoom in at this point. Do you see what happens, guys? The line is even more steep. Yes? And as you zoom in here, look at it. You see that the line gets vertical. It gets very steep. Yes? Now, if you were to zoom in at this point, at the tip, look how sharp it is at the tip. It cannot even graph the sharpness. It's extremely sharp at the tip. It would cut you tremendously bad. So that's the worst non-differentiable behavior at a point that you can have. Well, one of them, I suppose. That's pretty bad, because the slope does not exist at all. You understand, guys? Okay, so Francis asked me why does sharpness matter? Look at it. If you zoom in at this point, does it ever look like a straight line segment? Does it ever look like a straight line segment? No, it looks like a broken line. Yes, if you zoom in at the tip. No matter how much you zoom at the tip, it does not look like a straight line. Yes? And that means that the derivative, the limit, if you don't have a straight line, there's of course how you cannot calculate a slope for it. The derivative is just the slope of the straight line that you will see. Guys, do you understand why the derivative is the slope of the straight line that you will see? Do you get it? Or you don't see it? Yes. So here is that wedge. Here is a wedge. So the function is defined as 1 plus x if x is less than 0, and 1 minus x if x is bigger than 0. Guys, without doing any calculation, can you tell me what is? Let me just that's a comprehension check. Tell me, please, what do you think is the derivative at this point? If I zoom in, I will calculate what derivative there without doing the limit. Okay. Well, exactly. If you understood, guys, that's the point. If you understand what the derivative is, you just look at it and you right away know what is the derivative, what is the limit, right, of this function at this point. In other words, you see, I'm asking you without doing any calculations. Tell me, please, let's say this point is minus 1. Tell me, please, what is limit as x goes to minus 1, f of x minus f of minus 1 divided by x minus 1. You understand? That's what I'm asking you. Tell me what this limit is equal to. And without doing anything. Without doing, you know, the algebra. No, I said at minus 1, not at 0. Not at 0, at minus 1. What's the derivative at minus 1? Exactly, Christiana. Exactly, it's 1. Now, why is it 1, guys? Look at it. If you zoom in at this point, in particular, you're zooming in at a local line segment. Now, what is that local line segment? It's a local line segment that is this entire thing. That's what you're going to see, the same line segment, yes? If you zoom in at a line, no matter where you zoom in at a line, that small tile of that line is just that same part. And it has the same slope as the full line. Do you agree? You understand what I'm saying, guys, right? When you're calculating derivative, you're calculating the slope of the microscopic line segment. But the microscopic line segments are aligned, right? The tangent line to a line is that same line. Do you agree? Because again, guys, if you understand geometrically what the limit means, it means zoom in and you will see a line. What happens if you zoom in at a line to begin with? You're going to see that same line. Yes? So the slope here, guys, will be 1. How do I know it's 1? Because, well, here you can see this is the line. Sorry, so this is the line if x is less than 0. And that line has slope 1. You can see it in front of the x. And what would be the slope anywhere here? -1, very good. You can carry out the calculation if you want to, but that's obviously going to be the slope. Yes, here I actually bothered and carried the calculation explicitly, but at 0. Now what happens if I zoom in from the right? If I zoom in from the right, it means that I am seeing, here is my edge of the screen, and I'm zooming in from the right. I will see that the slope is -1. And here I carry out that calculation. Look at it, zooming in from the right. Of course, the slope is -1. If I zoom in from the left, on the other hand, then I will see what slope? I will see the slope 1. I do the calculations if you care, but it's obvious. You agree? Because when I zoom in from the left, x is in here, so I'm measuring a slope from this point to some point in here. So I'm measuring the slope along this line segment. And so the left and right edges do not match. The slope does not exist at 0, which is obvious. It's made of 2 distinct line segments. When you zoom in at this edge, there will not be a slope. It will not look like a straight line there, ever. Okay? Now here is my question, guys. What do you think? You see, so this example is, we have non-differentiability only at this point, right? The function fails to be differentiable at 0, but it's differentiable everywhere else. Yes? If I have, can I create a function that's not differentiable on infinitely many points? Can I do that? So it's not one point where it's not differentiable, but there are infinitely many points where it's not differentiable. Can I do that? And you don't always have to write the explicit formula of the function. You can kind of imagine a drawing, right? Because a drawing could correspond to a formula. Yes, we can, right, guys? So I can do something like this. I can just make, I like the word in German, it's called zackig. So this is very zackig. Right? It's very zigzag, right? So it looks like teeth. Yes? So you can see where is this function? It's made of line segments. It's not going to be differentiable here, 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 here. It's where the line segments are joined. It's continuous graph, or in other words, it's a connected graph, one connected object. But if I zoom in at the vertices, I will not see a straight line, and therefore there will not be a slope there. Clear, guys? I want you to understand 2 things, guys. I want you to understand the relationship between the derivative slope and zooming in. You have to see it. You understand? Not just because you might forget, oh, I zoom in and I see a straight line, and then you forget why. That's the tangent line. You have to see the connection. You zoom in, that means that you see less and less of the x-axis around that point. That means the x-coordinates are very close to the x-coordinate of the point P, which is exactly the limit of the slope, the limit of the secant line. You understand now, Erison? Now, guys, here is another challenging question, maybe more challenging. You see that we have here infinitely many points of non-differentiability, but you agree that if you look a little bit to the left and a little bit to the right, yes, look a little to the left, look a little to the right, and you will see that if you zoom in to the left, zoom in to the right, you will see a straight line segment. It would be differentiable. Those points are isolated. In other words, here I found a point where the function isn't differentiable, but move slightly to the left and slightly to the right, and you will see that the curve becomes differentiable there. Is that always the case? Or can there be a function that's continuous everywhere, always continuous, but differentiable nowhere? Is that possible? Do you understand my question? In other words, it's one connected graph, but nowhere, no matter where I zoom in, it never looks like a straight line. Well, a circle, when you zoom in on a circle, you're on planet Earth. When you zoom, why did people think it's flat? That because they understand it's differentiable. It's a two-dimensional, it's a surface, right? So the surface of the planet, the differentiability there means a plane. All right. I mean, it depends what you mean, of course, by planet Earth. You have to be more precise, naturally, right? If you think of planet Earth as a ball or as a circle, then yeah, circles are definitely differentiable shapes. Do you believe me, guys? The circle is differentiable, yes? Or you don't? Zoom in on a circle, you see a straight line. That's all of modern history, guys. If you don't see it, then why would you laugh at the flat earthers? So, you understand my question, guys? Can there be a function that's continuous everywhere and yet fail to be differentiable at any point? Yes. Can you describe something like this, or can you imagine it? So let's see if I, first of all. Here is, guys, by the way, just to enforce it, here is part of the circle, right? Let me zoom in at this point. You see? Oh, oh, differentiable. Zoom in at another point. Let's say zoom in here. I will see a straight line. Whoop, differentiable. Can you think of anything that might not be? But be careful. There are sharp points, but you understand what I'm saying, guys. There are many things that have sharp points. Like, let's say this graph has sharp points. You agree? It's not differentiable at those points. But if I look a little bit to the left or a little bit to the right, here I'm looking to the right, it's differentiable here. Differentiable anywhere until I reach this point. So those points are isolated. You see, all you have to do is shift my view ever so slightly from a point, zoom in, and it will be differentiable. Are there functions that are continuous everywhere and differentiable nowhere? You were not going to the aquarium when you were children, because if you did, you would have met me. Do you know New York Aquarium, guys? Do you? They used to have a lot of different fish and sea life until I started working there. Then the dolphins disappeared, the penguins, certain sea lions, right? I just needed to provide for my family. I worked at the New York Aquarium. And guess what was my specialty? I used to talk about which particular creatures. Can you guess? Was I near the fluffy otters? No, I was not with it. Oh, good, Christina, exactly. Shark and horseshoe crabs, because I never liked children. They go, does it bite? And I don't want to be bothered. And, you know, I would prefer to work by the very cold water, because especially in the winter, they would bother me less. And I would see, my timer was the sea star. And when the sea star walked from one edge of the touch pole to another, I knew I can go home, right? I could just see it walks very slowly. It's very nice to watch it. It's like a timer, right? It begins at 8 a.m. and by the time it's 5 p.m., it's at the other edge of the aquarium and I can go home. And also they had those horseshoe crabs. Girl, do you want to touch a horseshoe crab? No? Goodbye. Leave me alone, right? And of course, then I worked with sharks. Have you ever seen the tooth of a shark? Have you? it's not the point that it's just very sharp. If you actually look at the tooth of a shark, guys, this is what it looks like. It's serrated. You understand? So if you look at the tooth, it's like essentially a triangle, and on top of it, there are many small triangles. And if you zoom in on those small triangles, there will be an extra layer of small triangles on top of that. No matter how much you zoom, there are triangles upon triangles upon triangles. You see, of arbitrarily small size. It's beyond the course of our class to show that you can make a formula like this, but you can. I can try to show you maybe how they look on the internet. They kind of, you can make something that looks like this. Do you see it? What you do is you take this triangular shape and you superimpose more and more triangles. And no matter how much you zoom in at any location, it will be serrated. Naturally, you cannot graph this function. You understand? I mean, it's just, it's very complicated. But you can mathematically describe it and mathematically show that when you zoom in, you will see more, you know, no matter how close you zoom in, you're going to see this zigzag pattern. Yes? So here you go, guys. Right? So you connect your thoughts. Here I see sharks and I see that it translates to mathematics. So that's pleasant. You know, and something from my experience allows me to realize that something is true mathematically. Also, sometimes something mathematically allows you to know that something is true in the real life. Good? This is the function. You see, I kind of made a crappy, sorry for the, I'm tired, right? For the kind of bad drawing, but you see what I mean? You zoom in at any segment and it would have more and more teeth on top of it. Okay, let's do some comprehension check, guys. Are you ready? Are you with me still? You're not exhausted, right? You have such a great understanding of calculus. You are so fascinated. You never knew it would be so easy. So tell me, please, here is my function. It's 5x plus 2. And I want you, without doing any calculations, tell me, please, what's the derivative at x equal to minus 7? Like, it should be like this. Okay, beautiful. It is 5. Because when you're asking for the derivative, guys, amazing. Some of you understand it. When you ask for the derivative, you're asking, if I look at this curve and I zoom in, will I see a straight line? And if I do see a straight line, what's the slope of that line? Yes? Now, the object I'm zooming in on is itself a line already. Do you see that? 5x plus whatever number, doesn't matter, it's a line. So when I zoom on it, I will see that the line segments, the microscopic line segments, are already aligned along the same line. And I'm always seeing that same line in the same slope. Good? I hope you understand, guys. It bothers me, right? You understand that you zoom in, that means you see less of the x-axis, which means x is close to the point, to the x-coordinate of the point you're zooming in at, which indicates mathematically that the slopes you calculate will be very close to the derivative slope. That's how I know that it will be the derivative that I will see. You see that, guys? Angelo, sorry, do you see it?
Yeah.
Good. You just, I saw you frown, so I thought maybe something bothers you about it, but you see it, yeah? Okay. Now, later on, you see, this is what I will mention. I will not bother you just today. You understand that when you go to Calc 3, and of course, all of you will go to Calc 3, you change perspective. You see, what's so important? What's important, slope is a little bit weird. Look at it. I look at a line. Look at it. This is a horizontal line when my eyes are this way. But if I tilt my perspective, the line no longer looks horizontal. And from my different perspective, will have a different slope. Do you agree? So geometric perspective is what always constant. No matter what perspective I look at a line, it looks like a line. So later on in Calc 3, it's much more convenient to define the derivative to be the actual line, geometric line. You understand? And not think about the slope. For us, for Calc 1, the derivative is the slope of the tangent line, but in differential geometry or later on, it's just more convenient to speak of the actual shape. And you just say, well, the derivative is the tangent plane or tangent line without mentioning its slope, because slope is just communicating your perspective to that line. Let me try to say maybe one word about it. Look at it, guys. Do you see this, guys? You see this line I drew here in the black XY coordinate? You see in the black XY coordinate, this black line, this one, right? Looks like it's the equation y equals x. But if I switch it to a green XY coordinate, look at it, the green x is parallel to that black line. So now it looks like that same thing has the slope 0 times x plus 1. That's the equation. So it looks like the line y equals 1. You follow what I'm saying? So when you speak of a slope of a line, you're truly communicating not only what shape you have, but your perspective when you look at it. So the derivative, much more broadly, is just a straight line segment. If you can change perspective, essentially that tells you that there is only one line. Right? You say this is a line, that is a line, but that's just a change of perspective. And you just have line, or you have a circle. You understand? And I will show you guys that if you understand change of perspective, you will immediately understand, if you know how to take the derivative of x squared, you will immediately know how to take the derivative of root of x. You see, the benefit of understanding that I can change perspective, I can right away know that if x squared is differentiable, then root of x is differentiable, and find the slope without doing any effort immediately. You see? And that will be later on a discussion. I will explain that later. I don't want to talk about it just this very moment. I will just give you a flavor of that later on. You see this? I'm showing you how the graph x squared and the graph root of x are related. All right, guys. So let's stop the lecture at this point. It's at 3:30 that we are done, right? If you are interested, I have a what, when, where, because you're English speakers, one question will be easy for you, and the second question will be remarkable and interesting, and not easy. Okay, but you have one question where you might be able to answer it correctly.